All right, we're going to do one more Dalton's Law problem. This pertains to your lab this week. This is uh, collecting. I'm sorry, not this week. I think it's next week. Collecting a gas over water. And I just want to say before I get started, I hope it is as beautiful outside wherever you are as it is here at my house, because it is fantastic, about 80 degrees, sunny, little breeze, and I hope you guys get outside and go for a walk while staying 6 feet away from everybody. And just enjoy some of that nice spring weather. Do not sit inside and just watch TV, stream Netflix, whatever. Anyway, so collecting a gas over water is common because we can use gas to kind of exclude other gases. So the scenario here is we have a flask. It could be a test tube, could be anything. And in that flask, we'll have some HCl. I like to make HCl red. And then we're going to add a piece of zinc. And then we're going to get some bubbles off of that. And those bubbles are going to be H2 gas. Okay, and we're going to have a stopper in this thing. And we're going to have a hose. I'm just going to draw the hose like that. But it's a rubber hose. And it is going to be connected to, or I'm sorry, it's going to be going up into, this doesn't look very long, but it's a gas collection burette. And here we have a beaker, and inside the beaker is water. So the way this works is at first this thing is completely filled with water. Okay, completely filled with water. Then the gas bubbles start to bubble up, and what we get is we get H2O liquid here, and then this is the H2 gas. Okay, but excuse me, but what happens is some of that water evaporates. You know, if you leave water sitting out, it will evaporate. So we also get some H2O gas in here. Okay, and Dalton's law of partial pressures tells us that the pressure inside of there, the total pressure, is equal to the pressure due to hydrogen plus the pressure due to water. Okay, and we kind of make an assumption. We do, well, it's a pretty good assumption. Let's just put it that way. We say that the pressure, the total pressure inside, is equal to atmospheric pressure, P sub ATM. And now we can just get off a barometer. That's what we do in lab. And in lab, you won't do it because, hey, you're at home. But what you would do is you would kind of equalize. Remember that this height difference here exerts pressure. Even though water is not as dense as mercury, it still exerts pressure. It's 1/13 the pressure that it would be for mercury because water is 1/13 the density. But that height kind of messes with your pressure. So there's a way to normalize, basically bring this water level down to that pressure, but we're not going to get into all the hairy details of how exactly you do it in lab. But we're just going to say that P total is equal to the atmosphere, so we make that simple substitution and we get the atmospheric pressure is equal to the partial pressure of hydrogen plus the partial pressure of water. Okay. Now let's just say we collect 78.0 milliliters of H2 gas at 25 degrees Celsius and 753 millimeters of mercury. And we want to know what mass of H2 is collected. Okay. Well, if we take that equation up there in yellow, that guy right there, let's bring him down here. P sub ATM is equal to P sub H2 plus P sub H2O. We're really interested in the pressure of hydrogen because that's the gas we're interested in. We don't care about the water. So what we do, just rearrange this, P sub, rearrange it, P sub H2 is equal to P sub ATM minus P sub H2O. And where do we get this value? Same value. We look it up. And we'll find that the partial pressure of water at 25 degrees Celsius is equal to, where in my notes is it? 23.78 millimeters of mercury. Okay, now why does it matter what the temperature is? Well, you all know the higher the temperature, the faster the water evaporates, and that means the partial pressure is higher. The lower the temperature, the slower water evaporates. That means the partial pressure is lower. So partial pressure is dependent on temperature. So all we have to do is plug in. So P sub H2 is equal to, that's our atmospheric pressure, 753 millimeters of mercury, minus 23.78 millimeters of mercury, and that gives me 729 millimeters of mercury. That's my pressure of H2. Now, all we need to do is PV equals nRT. What are we solving for? Solving for mass. Mass isn't in here, but moles is, and we know the identity of the gas. So we can easily make that substitution. So take our 729 millimeters mercury. Our volume is 0.0780 liters. R, I'm going to use 62.4 liters times millimeters of mercury over Kelvin times moles times my temperature of 298 Kelvin. And what we come out with is 0.00306 moles of H2 gas. However, the problem asks for mass, so now all we have to do is take our mole, 0.00306 moles of H2, and times 2.016 grams of H2 per 1 mole of H2, just the molar mass of H2, and we come out with 0.00616 grams of H2. Okay, but the key is that partial pressure of water, actually right there. And just in case you're curious, Dalton's law of partial pressures has lots of applications. Deep sea diving they talk about in your textbook. But if you ever go into the medical fields, when you do gas anesthesia, partial pressures are important there, as well as for oxygen saturation. You know, a lot of people with COVID-19, their oxygen saturation in their blood is down. So we need to increase the partial pressure of O2 that they are receiving, so we put them on oxygen. Okay, and that increases the partial pressure of O2. And we'll talk about solubility of gases in a different chapter.